Let's look at about 4 more examples, run through some additional little variations and techniques that you might run into, some things that are not necessarily difficult, but there's some things that might catch you off guard if you aren't expecting them and haven't seen how to deal with such things. Let's take a look at number 52. We have the integral of x squared times the square root of 2 plus x dx. An obvious substitution is to let u be the stuff that is inside the radical. So we'll let u equal 2 plus x. Then du, derivative of 2 is 0, derivative of x is just 1, so the differential du is equal to dx. So we have, oh, actually I don't want to close that off just yet, do I? No. So we have that. So we start looking at our integral here. And, okay, so we have this square root of 2 plus x, that'll become a square root of u. Dx is equal to du, that's great. What about this x squared? That's not accounted for, is it? But, looking at this expression here, if u is equal to 2 plus x, that means that x is equal to u minus 2, right? Just simple algebra there. So that means that x squared becomes u minus 2 squared. Okay? This is just a thorough translation. We change everything to be in terms of u. So now let's start working this out a bit. Let's expand this. We have u squared minus 4u plus 4 times a u to the 1/2 power du. So distributing this through, that is u to the, let's see, that's 4 halves, so we get 5 halves, minus 4u to the 3 halves, plus 4u to the 1/2 power du. Now we can take an antiderivative. We have u to the 5 halves. We need to add 1 to that to make 7 halves. We can divide by 7 halves, which is the same as multiplying by the reciprocal, 2/7. Minus 4 times, we have u to the 3 halves, add 1 becomes 5 halves, so we can multiply by 2/5. Plus 4 times u to the 1/2, adding 1 gives us 3 halves. Divide by 3 halves is same as multiplying by 2/3. Plus a constant. Okay. So this is 2/7 times, let's see what u was. U is equal to 2 plus x. So that is 2 plus x to the 7 halves power. Minus, simplifying this fraction, we have 8/5 times 2 plus x to the 5 halves power. Plus, and that looks like 8/3 times 2 plus x to the 3 halves power plus a constant. And I'm just glancing at my notes to see if that came out correctly, and yes, that looks good. There we are. It's a little bit ugly, but if we did everything correctly, it should work. And if you aren't sure, and you really want to make sure, you can take the derivatives of these things and algebraically simplify. You might have a little bit of algebraic work ahead of you to do all these simplifications and cancellations, but you should in the end find it simplifying down to that expression right there. Okay. So this is the idea here, is when we do a substitution, you're expecting a certain expression to be replaced by u, and you're expecting some other things to be handled by the differential, but sometimes there are still some parts that are not taken care of that way, in which case, you just have to sort of deal with those. Let's look at a problem that is somewhat similar. Number 54, we have the integral of x cubed times the square root of x squared plus 1 dx. There are a few differences, though. Let's again start off with the obvious substitution of u equals x squared plus 1. I say obvious because we have a square root, so it's natural to take what's inside of that, the radicand, as our variable. So then du, differentiating this to get our differential, if u is x squared plus 1, du is 2x dx. looking through here, we see that we don't have a 2, so I should divide that over. That's going to be a 1/2 du is equal to x dx. Instead of x, we have x cubed, right? So let me separate things a little bit. X cubed is equal to x squared times x, right? Now the x squared plus 1 is equal to u. We can substitute that. X dx together is 1/2 du, but that doesn't account for the x squared yet. But we can do something similar as before. If u is equal to x squared plus 1, that means that x squared is equal to u minus 1, right? So plugging all of these things in, we have a 1/2. X squared is u minus 1. We have a square root of u, and x dx gives us the du with that 1/2 that I put out front, right? So this is 1/2 times the integral of, that's a u to the 1/2, so we have u to the 3/2 minus u to the 1/2 du. Let me separate that so it doesn't look like it's part of these. So we have 1/2 times u to the 3/2, apply the power rule to integrate, we get u to the 5/2 times 2/5, minus, we have u to the 3/2 times 2/3, and we need a constant at the end. I'm just imagining distributing that 1/2 into the constant, so we have that taken care of. Now we want to do a couple of things to further simplify. Let's distribute the 1/2 through, so this becomes 1/5, and also, we think about what u was. U is equal to x squared plus 1. So we have x squared plus 1 to the 5/2 power. Minus, distributing the 1/2 through, we get 1/3. U is x squared plus 1 to the 3/2 power. Okay. So there we go. There's our final expression. Now, sometimes we have more than one option for a substitution to apply. Okay, so let me see how much space I have up here. Let's come back up here. This is the, like I said, the quote-unquote obvious substitution. This is the one that I would probably do if I were working with this myself. But if we play around with this a little bit more, we can experiment. And sometimes experimentation pays benefits, pays, you have a return on the, I don't know what idiom I'm looking for there. Let's look at what happens if we instead let u equal the square root of x squared plus 1. Okay. Now, at first this looks like a worse idea, because when you take the derivative, you have your 1/2 power of that thing times the negative, to the power of negative 1/2 times the 2x from the chain rule and blah, blah, blah. But if we square both sides of this, we find that u squared is equal to x squared plus 1. Okay? And we can see a few things from this. One is that, again, there you have this x cubed that we expect to have to split into an x squared and an x. So, we can easily see that x squared is equal to u squared minus 1. This u is different from this u, so don't worry about this not matching the other expression. The other thing here, when we take our differential, if we do this sort of implicitly, we can, if we take sort of the differential of both sides, like implicit differentiation, we would have 2u du is equal to 2x dx. And then simplifying, we have u du equals x dx. Okay? Which means that this integral here, let's take this integral, the one where we've written out the x squared and the x's. What we would have there is the, let me rearrange things a bit. So that is x squared times the square root of x squared plus 1 times x dx. X squared is u squared minus 1. the square root of x squared plus 1 is equal to u, and x dx is equal to u du, right? So now, when you simplify this, we have a u squared here, we get a u to the fourth minus u squared. You'll note that I no longer have those fractional powers, right? And this is much easier to manipulate and integrate, get an antiderivative. Now, there's no such thing as a free lunch, as they say. You're not getting rid of the radicals. In the end, when you substitute back to get in terms of x, that radical comes back in. So your answer, I leave it to you to finish this, but you can confirm for yourself that the answer does come out to be this in the end. We're not making the answer simpler. But some of the intermediate work happens to be a little bit simpler. Now, in this particular problem, unless you have that stroke of inspiration, is it worth it? Maybe not, right? The risk of experimenting like that and then fiddling around to get these things, it saves a little bit of work, but maybe not enough to be, especially on like an exam in a timed circumstance. Maybe don't take chances, do the thing that's obvious that will work out. But there are problems where this significantly simplifies the work. So, just keep that in mind. Be prepared to kind of think outside the box, as it were, and take some risks, right? If you're not under time constraints and you have a weird integral to deal with, maybe play around with it a little bit. Even if you do a substitution and it does work, if you didn't really like it, if it was kind of messy, try some other substitutions and see if those work any better. That's a great way to learn and improve your skills and develop some techniques that you might apply in the future. So yeah, some possible like algebraic manipulations that might show up there. Let's take a look at this example here with the integral of dx over the square root of 5 minus x squared. Now remember that this is another way of writing a 1 over the square root of 5 minus x squared times dx. So if you want to think about a 1 in the numerator, that might help. If we try an obvious substitution like u equals 5 minus x squared, then du is negative 2x dx, and there's no x any place for us to work with, so that doesn't help. Even if you try isolating the dx, what you end up introducing is there's a divided by x, but there's nothing you can do with that x. If you try solving for it and plugging in, now you just get a messy radical, and you've gone back to where you started and you just made it worse. So that doesn't really work out. Maybe you try something fancy, like what I did before. Okay, well, maybe u is equal to the square root of 5 minus x squared. Let's make it the entire denominator, right? So then u squared is 5 minus x squared. We have 2u du is equal to negative 2x dx. But again, we need the x with the dx, so that doesn't work either. Okay. So here, the easiest approach, I think, is to think about, okay, we're trying to find an antiderivative. What derivative form does this most closely resemble? And it might not look like a lot, but remember that we can do things with constant multiples as far as substitutions are concerned. So if this is a 5 or a 9 or a 1 or 100, we can massage this and do things with those constant factors and see what we can work out of this. If this were a 1, and we have 1 over the square root of 1 minus x squared, that hopefully you recognize as a derivative of an inverse trig function, right? So let's start working on the algebra that would be necessary to get that to be a 1. And I'll do this step by step. We factor out a 5 forcefully from this. We have 1 minus x squared over 5 inside the radical, right? And I'll go ahead and put the dx, the 1 at the top, and the dx afterward to start making this look like what you might expect. So this is the square root of 5 times the square root of 1 minus x squared over 5. But that x squared over 5 we can write as x over the square root of 5, quantity squared. Yes? all of this is still in the denominator. Right? So, I'm just thinking for a moment about which way is the best way to organize this, but I guess we'll figure it out when we work out the substitution. We have this here. Let's let u equal x divided by the square root of 5. And you know, I'm gonna make life just a little bit easier on myself, have fewer fractions to deal with. I'll multiply that square root of 5 over, so the square root of 5 times u equals x. So then the square root of 5 du equals dx. So this becomes 1 minus u squared, and this is still all in the denominator under 1, times dx. Dx is equal to the square root of 5 du. Fortunately, we can actually kind of simplify, right? Square root of 5 over square root of 5 is 1. So we have the integral of 1 over 1 minus u squared, square root of 1 minus u squared, I'm sorry, du. Which again, hopefully you recognize as an inverse trig function. That is the derivative of arcsine. And substituting back in, we have u is equal to x over the square root of 5. And there we go. That might not be apparent from what we started with, the integral of dx over the square root of 5 minus x squared, but that turns out to be the arcsine of x over the square root of 5. And again, you can check this, take the derivative, simplify, make sure you get back to the original integrand if you wish, and confirm that works out. So this is kind of an idea here. Arcsine is, of course, not the only function we can do this with. A lot of functions that have derivatives in kind of fixed forms. So arctangent is, another example. If you have, a 1 over, if you have, well, let me put it this way. If you have any constant divided by, let's say a constant plus some quantity squared, depending on what this quantity is, and maybe it doesn't even have to be a constant, right? This could be, depending on what this is, we might need its derivative. So let me change that from an a to a u to represent some general thing. A form like this, you might consider, well, maybe an arctangent could work, right? So you could divide out whatever this constant is to get into the form of like 1 plus whatever this thing comes out to be squared, and then do your substitution or whatever else. So sometimes we need to be, not everything is so clean and elegant that things just fall out for us. Sometimes we have to kind of force things a bit. We try to recognize, okay, what structure does this resemble? And can I make it be that structure by doing some algebraic manipulations and forcing it to get into the form that I want? So, that's a technique that can be useful frequently from time to time. One last example, number 72, we have the integral from negative pi over 3 to positive pi over 3 of x to the 4th sine x dx. You can try a variety of substitutions here, and probably none of them are going to work. This calls for a different technique, something slipped in at the end of this section. And when we see something that is difficult to integrate, or actually, let me back that up. When you see bounds that are symmetric around 0, right, plus and minus a constant, you want to ask yourself the question of whether the function itself has any particular kind of symmetry. Let's let f of x be x to the 4th sine x. Okay. And if this has any kind of symmetry, hopefully this is either even or odd. So let's try it out. F of negative x would be negative x to the fourth times the sine of negative x. Negative x to the fourth power is the same as x to the fourth power because negative 1 to the fourth is a positive 1. Sine of negative x is negative sine x. So this is equal to the negative of x to the fourth sine x. And that is equal to the negative of f of x. Therefore, this thing right here is what we call an odd function. If we were to graph it, we get something very crudely speaking. This is not going to be great, but very crudely speaking, we get something sort of like this. If we graph it from negative pi over 3 to pi over 3. And this integral can be interpreted as the signed area. Since this function is odd, it's perfectly symmetric about the origin, which means that this positive area and this negative area are equal in magnitude, so they cancel each other out. And this integral is equal to 0. So a weird 0 that had a little tail that I was not expecting. What is happening here? There we go. 0. Yeah. This problem is rather... It's a little challenging to do by hand. In Calc 2, you will learn a technique called integration by parts. And if we apply the technique of integration by parts 4 times successively, we can grind this down and find its antiderivative, but it's just going to work out to be 0. Now, this technique only works because of this symmetry, right? If these bounds were not equal but opposite, then we would have to do that other technique, like I mentioned, integration by parts. You're not prepared for that yet. We won't ask you to do that yet. It's a lot harder. But in this case, because of the symmetry of what we're evaluating, it happened to be very nice and easy and clean. And again, that's also only because of the type of symmetry, right? This is an odd function. If we had had a similar problem, but with an even function, so maybe we had x to the fourth cosine x dx, then the best we could do with this is say that, okay, well, that is twice the integral from 0 to pi over 3 of that thing, which is helpful, but it still doesn't do it for us, Take a look at the figures in the textbook for some prettier pictures that illustrate why this is the case in terms of these symmetries. But of course, the idea is that with an even function, it's the same on both sides, so you're just doubling whatever one side is. But because this was an odd function, and also the bounds were symmetric around 0, so we were integrating over an interval symmetric about 0, those two facts together combine to make this an extremely simple integral to evaluate. So be alert to that. If you see symmetric bounds, check to see if the function is odd, because if so, you can just state the function is odd and that the answer is 0. If you want to be really clear, you could say by symmetry. It's not really necessary, but it is nice. It's kind of a good style. The integral is equal to 0 by symmetry. But you do need to make sure to check those conditions, right? Just because it's symmetric does not mean it's going to equal 0. If this is a function that is neither even nor odd, then the symmetry doesn't help at all, and you just have to work through and evaluate it. And even if this is a function that is easier to integrate, you can still apply this. That can save you some work, right? I don't think they would get this tricky on the exam. I don't usually see this on final exams. They try to make them a little more straightforward, but like, a classic type of sort of trick problem is to give a messy integral that you can grind through in like half a page or a page of work, and it just comes out to be 0 at the end, which you could have done in like one line if you had recognized that at the beginning. There are a lot of things in practice that show up to be symmetric, so be alert for that in other contexts. I'm not just talking about calculus classes. I'm talking about other places where you see integrals when, a lot of symmetries happen in nature. So if things like this happen, look for those opportunities.